When you look at a face, you see a person, right? You see their history, their emotions, all in just a fraction of a second. But when a computer looks at that exact same picture, it sees, well, it sees nothing, just a silent, shimmering ocean of numbers. So how on earth do we teach a machine to bridge that gap, to go from numbers to actually seeing? Let's dive in.
I mean, really think about that for a second. The device in your pocket performs this little miracle of perception, like dozens of times a day. It feels totally like magic, but it's not. It's the result of one of the most incredible fields in AI. So what is really going on behind that screen?
And here it is. This is the core challenge right here. On the left, that's our world. It's holistic, it's intuitive, it's immediate. And on the right, that's the computer's world, just a cold, logical grid with millions of numbers. The entire story of computer vision is about bridging this huge, huge gap.
That bridge, it actually has a name: computer vision. It's the whole science dedicated to moving beyond just, capturing an image, to actually interpreting it. It's all about turning that sea of numbers into something meaningful, something the machine can actually understand and act on.
So to understand how machine learns to see a face, we have to start at the very beginning. We have to understand the language it speaks, and that language is written in pixels. To a computer, any image, I don't care if it's a photo of your dog, a beautiful sunset, or your own face, it's nothing more than a structured mosaic. Just imagine a giant silent canvas, where every single tile is just one single point of light. That's what a computer's looking at. And here's the key thing. To a computer, a pixel isn't a color, it's just a set of instructions. For a color image, that's usually 3 numbers that represent the intensity of red, green, and blue light. So the computer doesn't see sky blue. Nope, it sees a coordinate with values, something like 135, 206, 235. That's it. Now the scale here is it's colossal. A single high-definition photo means the computer is staring at what is basically a spreadsheet with over 2 million rows. So the first absolutely monumental challenge is this: how do you find a human face, an eye, a nose, a smile, in that overwhelming ocean of data?
So how did we first even try to solve this? Well, the early pioneers, they took a very direct approach. They tried to give the machine a fixed rulebook, almost like a checklist for what a face is supposed to look like.
This was the whole era of what we call handcrafted features. We had algorithms like Hog and Sift, and basically engineers would write code telling the computer exactly what to look for, specific geometric patterns like edges and corners. It was literally a checklist. Find 2 dark ovals here, then look for a vertical line just below them, and so on.
But here's the fatal flaw. What happens if I tilt my head, or if I walk into a shadow? All those rigid, human-defined rules, they immediately shatter. The whole system just falls apart. This approach was way too fragile for the messy, unpredictable real world, which meant the entire approach had to be thrown out. A revolution was needed.
And that shift wasn't just an improvement, it was a true revolution. It completely changed the name of the game.
See, instead of engineers hand-coding what features to look for, we built systems that could learn how to find the most important features all by themselves, just by looking at massive, massive amounts of data. And the hero of this new approach, the engine that powered this incredible leap forward, is the Convolutional Neural Network, or CNN for short. It's a special type of algorithm that's actually inspired by the human brain, and it's specifically designed to process the world visually.
So how does a CNN actually work? Well, conceptually, it's designed to mimic the way our own vision system works, by building up understanding in a hierarchy. It starts with simple shapes and builds up to complex ideas.
Okay, so it all starts with something called convolution. Think of this layer as a team of tiny detectives, each with a magnifying glass, scanning the image for really basic patterns like edges and curves. Next up is activation, which acts like a gatekeeper. It decides which of those patterns are strong and important enough to pass along to the next stage. And finally, you've got pooling. This step is like a summarizer. It keeps the essential info but throws away the noise, which makes the whole system way more efficient and robust. When you put all these layers together, you get this incredible engine of abstraction. The scanner finds the basic lines. The gatekeeper filters out what's not important. The summarizer makes sure the system recognizes a pattern even if it moves a little bit. And finally, the synthesizer puts all those abstract pieces together to form a final, cohesive understanding. Hey, this is a face. This is the real magic of it all. A CNN learns layer by layer by layer.
The first layers might just learn to see simple edges. But then the middle layers combine those edges into more complex features, like an eye, or the curve of a nostril. And then the deepest layers learn to assemble all of those features into the complete concept of a face. It's brilliant.
So, after all this incredible processing, all the scanning, the filtering, the summarizing, what's the final result? What is the computer actually produced at the end of all this?
The final output is called a feature map, or sometimes an embedding. And honestly, the best way to think of it is as a unique digital fingerprint of the face. It's not a picture anymore, it's a dense string of numbers that mathematically captures the absolute essence of that face's geometry. The CNN's entire job is just to create this one perfect abstract summary.
So the computer has done it. It has translated the messy, complicated reality of a human face into a clean, unique mathematical signature. It has learned to see. But that raises the next huge question, right? How does it take that fingerprint and match it to a name and a database? Well, that is the story for our next explainer.